In this video, I would like to talk about the concept of a vector and scalar field. This is a depiction of a vector and scalar field. It's a visualization of a three-dimensional numerical model of the Earth. And in this left diagram, this sort of orangish ball is the core of the Earth. And the arrows right here show the motion of the tectonic plates on the surface of the Earth. Of course, the plates are moving very slowly, but very steadily. This blue figure here is a depiction of a hot upwelling. It's hot at the base of the core, and that hot upwelling is less dense, so it rises through the mantle, and then it hits the base of the tectonic plates, and it starts spreading outward around outward like a sort of like a pancake, I guess, an inverted pancake. This image shows a close-up of this hot upwelling. It actually represents so this hot upwelling actually gives rise to the Hawaiian hotspot and eventually the Hawaiian Islands that on the Pacific plate. And so there are two fields represented. The first is a vector field, and those are the velocities of the plates as well as the velocity of the mantle below it. This is a vector that varies in 3D space, that is x, y, and z. It also varies in time, which I'll show you in a bit. The colors on the bottom, I guess, sort of plane here is this temperature on the base of the mantle, or really at the core mantle boundary. So the blue colors denote relatively cool temperatures, and the orange colors represent the highest temperatures. Again, just on this surface, this patch of this spherical shell of the core mantle boundary. So this is one way to represent the scalar field temperature in 2D space. Another way to represent this scalar field temperature is by an isosurface. So this blue shaded feature is called an isosurface, and it's a three-dimensional surface over which the temperature is constant. Everywhere inside the surface, the temperature is hotter. Everywhere outside the surface, the temperature is cooler. So it outlines this hot upwelling as it rises and interacts with the base of the plate. Again, so these are two ways of representing a scalar field in 3D space. Now I mentioned these properties also vary in time. Time here is T is measured in million years ago. So this is a picture of a model of the Earth, or the Hawaiian mantle plume, 80 million years ago. And to display how these properties vary in time, I'll show a movie here. And what you'll see here, as the movie runs, the time is proceeding forward from 80 million years ago to present day. And as that happens, you can see obvious changes in the direction and rate of the plate motion on the surface, as well as the directions and rates of velocity in the mantle below it. In response to those changes in plate motion and mantle velocity, you can see the isosurface of the Hawaiian plume bending and swaying in this sort of regional mantle wind, as some people describe it. And as this hot upwelling moves with the flowing mantle, the surface expression, or where it hits the plate, also migrates beneath the plate. And that's representing, this is where the Hawaiian volcanoes would erupt over the last 80 or so million years. So this is also an illustration of how powerful mathematics and computational methods have become in simulating sort of somewhat realistic Earth-like processes. And if you get into this more, you'll see more of these such diagrams. You'll be able to interpret them, and perhaps you'll be even involved with producing some of these sort of state-of-the-art calculations or these numerical models. So the relevant section here is vector and scalar fields. And this is chapters or section 16.1 and 16.2 of Greenberg's textbook. So just to sort of define what a scalar field is, it's basically a scalar quantity that varies in 2D or 3D space. And in the example given here, the scalar field was temperature, and it of course varied in 3D space, and in fact it varied in a fourth dimension if you consider time as a dimension. So in 2D, a scalar field U would vary in X and Y, and those are often sort of illustrated or visualized as lines of constant values or contours. So again, we had this plane at the core mantle boundary. Here we depicted this two-dimensional variation in temperature with colors, but we could have also shown contours of constant temperature, and they would, in this case, look like concentric circles approximately. So these would be contours. You may be familiar with contours on a topography map, where topography is the scalar field. And then in 3D, U would vary with X, Y, and Z, can be visualized as a surface of constant value. And again, the surface we looked at here was this isosurface, which is a surface of constant value. So that's a scalar field. A vector field involves a vector quantity that varies in space. So for example, in 3D, a vector v in x, y, and z would be described as each component varying in x, y, and z. And if we're in a Cartesian geometry, which we're not in this case, but if we were in a Cartesian geometry, we would have the base vectors multiplied by each component. And there's various ways to display vector fields. In the example given here, we showed these vectors as arrows pointing in the direction represented at each point, as well as, in this case, as a function of time. So I hope this gives you a feel for what scalar and vector fields are, and a feel for how they might be represented visually and for interpretation. So this concludes this relatively short video, and it's an introduction to vector calculus and actually scalar and vector field theory.